Hey everybody, welcome back to another algorithm session. Today we're going to be continuing algorithm journeys with recursion, and this particular algorithm we're going to focus on doing recursive Fibonacci. We're also going to utilize a concept called dynamic programming and memoization, which basically is taking a larger problem, breaking it down to smaller chunks, and then solving those individual chunks. So with that, we're going to start. Here we go. All right, so we're going to first create our function. So we're going to say function fib, and we're going to pass a parameter of n. The first thing we're going to do is create a variable called memo, and this memo is actually an empty dictionary. And what's going to happen is, as we do our recursive functions, our recursive calls that is, those values, those results will be placed into our empty dictionary. Here we go. And so we're going to have let memo equals our open dictionary is right here. The next thing we're going to do is actually do another function within our outer function. So we're going to call this function rfib, plus pass another parameter of x. I'll tell you guys why I'm doing it this way, but there's a couple of other ways you can do it, but I just prefer to do it this way. The next sequence we're going to do is, with recursion, you always need a base case. And in the base case, it's pretty much your most definitive base bottom boy answer that you need. So for recursive Fibonacci, we actually need a couple of base cases. So we're going to say if x is equal to 0, we're going to return 0, close out of this, else if x is equal to 1 or x is equal to 2, we're going to return 1, close out of this. We also want to return if anything is in the memo dictionary. If we do have values, we want to see what those values are. Otherwise, it's just not going to return anything. So we're going to say if memo at index of x, meaning if we do have a value at the index of x, we're going to return memo at index of x. Close out of this. And this is where we get into our recursive calls. So we're going to say else. And then what we're going to do is we're going to actually put the results of our recursion inside of our empty memo dictionary. So else memo of x is equal to r fib x minus 1 plus r fib x minus 2. And then once we have these results stored into our memo, we're going to return a memo of x, close out of this. We're going to close out of our inner function. And then here we're going to return our fib. We're going to pass the parameter of n, and then close out of our main function. So there you go. This is our recursive Fibonacci. We have our open dictionary here that allows us to store values from our recursive calls. We have our inner function. We have our base cases. We are returning values if values already exist. If they do not, we don't return them. Otherwise, if we have no values, we're going to actually store the values from our recursive calls into our memo, and then we're going to return that. Close our function, and then we're going to return our recursive Fibonacci with the value of n. Now real quick, the reason I put memo here and not just have one function is because if we just had all this code block and just this fib n function, what's going to happen is every time it makes recursive calls and goes all the way to the top of the function to run its course, it's going to always set this to 0. So since it's already empty, it's already set at 0. We're going to do our call. We're going to store values and then come back up again. And it's going to set us up to 0 again. So in this case, what happens is we have some lexical scoping going on here. Basically, we have two functions. We have the outer function and the inner function. the inner function has access to our memo dictionary, but when it makes these recursive calls, it's going to only pretty much cycle through the inner function here and not really affect this open dictionary. The other thing we could have done is we could have made this a global scope variable, but I didn't feel like doing that because I didn't really want to pollute the global scope. So in this case, it's just nicely contained in this fib_n function. So this is our recursion. We're going to do a quick diagram to see how it looks. So our, let's say I want my target to be, let's say, fib of 8. So that's the number we're going to do. So what's going to happen is, when it makes these recursive calls, this fib of 8 is going to make a recursive call to the previous number, and then once it gets to fib of 7, it's going to make a recursive call to that previous number. So it's going to eventually wind up looking like this: 7 plus 6, and then this breaks down into 6 plus 5, plus this breaks down into 5 plus 4, and as you can see, a lot of these numbers, as we go down and further break it down, it's going to just all hit 1. If you'll notice, a lot of these numbers repeat. So 6 and 6 repeat, 5 and 5 repeat, and then of course 4. And then if I write 4 here, 4 and 4 will repeat. So there's a lot of number repetition. What we're doing here with this memoization concept is that we're going to place numbers in our empty dictionary, and then as the recursion continues to follow through, if those numbers repeat again, we're not going to place those repetitive numbers in the dictionary because those values have already been computed. We're just going to focus on the numbers that have not been placed. The reason I'm doing it this way is that it's for optimization, it's for efficiency, and it's for faster runtime. Of course, if you have like a fib of 7 or fib of 8, it doesn't really make a difference much doing this because you're not going to really save all that much time. But when you get into higher numbers like fib of 100 or fib of 1,000, then you get some really crazy large number of results. So that's when doing this type of with the dictionary and with the recursive calls, it saves you on runtime. So now basically, we have these numbers breaking down, making these recursive calls, and what's going to happen is the values from those recursive calls, as they go down the line, are going to come back up to the previous call that made it. So if 7 makes a call to 6, the values and the results from 6 are going to be sent back to 7, and then 7 is going to get those values and results and send it back to 8. So it's going to bubble up, if you will, with all these returning values. So we want to get to fib of 8. So fib of 1 and fib of 2 is pretty much our base cases. So we're going to start off that fib of 3, and that is 1 plus 1, which is equal to 2. And the way I get this is the fib of 3 makes a recursive call to fib of 2, so fib of 2 is equal to 1 plus 1. So these results get pushed back up to fib of 3. So fib of 3 is actually the results that have been returned from making a call to fib of 2. So now we go to fib of 4. And fib of 4 is equal to 2 plus 1, which is equal to 3. And we get fib of 4 by recursively calling fib of 3. So fib of 3 is 2 plus 1. Now this breaks down into 1 plus 1 plus 1. So this side is 2 plus, and the right side is 1. So now fib of 5 is the resulting values from fib of 4 plus fib of 3. So this would be 3 plus 2. Fib of 6 is the results from adding fib of 5 plus fib of 4. So that is 5 plus 3. Then we get to fib of 7, which is adding fib of 5 plus fib of fib of 6 plus fib of 5, which is 1 plus 3, and 3 plus 2, 5, which is 8 plus 5, which is 13. And now we get to fib of 8, which is adding fib of 7 plus fib of 6, 1 plus 3, 8, which is 13 plus 8 equals 21. So you see how we're constantly bubbling up with these values, and then our ultimate result is getting bigger and bigger. So once we get into higher fib numbers, this is going to really take effect and really maximize our efficiency. So there you go. Hopefully that explains a little bit about recursive Fibonacci. Again, I'll do my very best in the next couple of recursive algorithms to further explain in details. It's sometimes really tricky to do this because, it's just kind of like this really brain teaser of a concept. So again, with constant practice, do your research. There's a lot of really great information on recursion, closures, lexical scoping, and with more practice, you'll get the hang of it. Then you'll realize it's really not so bad. So thanks for watching. Now you're in the know, and I'll see you at the next one. Bye bye.